So Hyung Do is the first brave one who's taking the task of discussing Pheno for the ultimate colliders with unlimited imagination. So I'll give you the time.
Yeah, thanks for the introduction, and also thanks for the invitation. Roberto asked me to give a talk on this title, which was really challenging and ambitious. And I had time to think about it for a few weeks, but couldn't come up with anything special. So it's a little bit disappointing to the audience. I confess in advance. So I decided to cover the history that I made for several decades. And this history, it comes along with the discovery of the Higgs. So it will show where we are and what we are thinking right now. So I think regarding the ultimate colliders, everybody just mentioned this Globatron by Enrico Fermi. So this is kind of the largest collider we could imagine currently in the Earth. And then I read this book by Stephen Hawking, the famous book, and he just estimated the size of the colliders needed to prove the grand unified theory, 10 to 16 GeV. So it is not realistic in the sense that they just ignore this synchrotron radiation, which is huge. But if you just scale up the linear scaling relation between the energy and the size, then basically the solar system size would cover the grand unified theory. So in principle, you can imagine the size of the collider that we need. And then I just have to mention that this very famous public book, so-called Scales, by Jeffrey West, famous theorist, he just described all those biological phenomena. I mean, many biological objects with different size actually have their pumping rates to be almost the same, or there are many universal rules that you can derive from simple physical laws. And then he ended up with this very interesting observation that there is a singularity whenever some power law or exponential growth doesn't meet another innovation. So you are dead. And for our situation, I thought that it's very similar, that people are just begging for larger and larger colliders with a more expensive budget. But actually, since we are living in the Earth, and so we have a actual realistic cap existing, and therefore this game cannot be continued. So we need something else to overcome this boundary. Oh, what is the N? So I mean, this is happening for any social phenomena. So originally it was obtained from the versus the population crisis, but basically you can apply it to many places. And I think this collider case is not exactly exponential growth, but I mean the needed cost and needed size grows linearly. However, our resources are limited. So in that sense, it also applies. So for the main topic, where is new physics? We have 50 years of BSM. When I studied, when I entered graduate school in physics, actually, star model was taken to be granted. And Higgs, although we had to wait for its discovery for 20, 30 years, everybody considered that it should be there. And then everybody was working on BSM, meaning beyond the star model. And the only caveat was there is a nightmare scenario where only Higgs is discovered at the colliders and nothing else. And then all our endeavor for 20, 30 years are gone and no one knows where to go. And actually, this was what happened in our world. So why are we sticking to beyond the star model rather than the star model. And then, I mean, you can ask two questions. One is why, and the other is why not? And from my side, I was always educated in a way that you should find a theory which is really well motivated rather than explaining some phenomena by a single new particle. I mean, it's always very easy to explain something, some signal, by introducing one particle or one interaction. That's very easy. However, you have to be able to get the coherent picture or frame where all those things are consistently explained. So that's my spirit for looking for a motivated theory. And then there are the other direction, which is unmotivated, meaning that basically this motivation might be just a prejudice and it might be misread strongly. And then therefore, it's better for you to explore more freely, even in unmotivated way. And this trend became more and more popular these days. I see, I mean, last week I saw many talks and I would count it as unmotivated theories from my criterion. So in the past, it was very clear that we had to solve certain problems. Without solving the problem, if you introduce another particle or another interaction, that you had to feel guilty. But these days, it's better to invent new ideas and new particles, and whatever signature you might expect, always it is encouraged. So I think there are pro and con of each approach, but today I will focus on this motivated side, which is disappearing or fading away. So for unmotivated BSM, I would say this is based on the lamppost principle, meaning that since our collider is limited and anyway, we cannot find the particle which is extremely heavy or extremely weakly interacting. Therefore, it's better to focus on today's interest, meaning that what is below the lamp. I mean, if you're looking for the key that you lost, then the actual chance for being right at the lamp post is very rare. Nevertheless, I mean, that's the best you can do. And therefore, that's what you are doing. And I think that summarizes the current status of the community. So you should keep in mind that what you are doing is like that. And then going back to motivated BSM, I think this figure summarized well the status of the problem. So this is what is called the hierarchy problem or fine-tuning problem in one sense. So suppose that in the middle, there are many plus charged particles existing. At the same time, you know that you measure the electric field and find that electric field is close to zero. So this is contradicting to your ENM knowledge. So what would be the solution? And then on the left side, no, let's go to the right side first. So on the right side, you can easily imagine that there are equal amount of negatively charged particles, like a conductor, and therefore you are guaranteed to have the vanishing electric field, because no matter how your charges are distributed, always you have the others which are canceling it, and you will end up with the conductor with the vanishing electric field. So this is a kind of naturalness criterion, or the symmetry that we are looking for in particle physics for 50 years or for many decades. And this was really successful till we encounter the Higgs boson. And then on the left, there is a multiverse argument or just the statistics. So there are so many samples, and then in one occasion, the random negatively charged particles just exactly cancel the plot charges that you measured or you observed. And then, is there any symmetric region? No, just you have enough ensemble or enough events that would be sufficient enough that Among them, just one will have nearly vanishing electric field. So these are two directions that people pursued for the Higgs mass. I mean, why the Higgs mass is so small compared to the Planck scale or any other scale that we encounter in physics. And then I would say that today, even I would come up with something in between or the third way. So for possible candidates of motivated BSM, I would classify this way. I mean, this is along the way that I pursued my research, and especially I will focus on some young ideas, meaning that supersymmetry and compositics or technical, that was there for 30, 40 years. And then I'm trying to explain you something less than 20 years, 15 years, 10 years. So regarding the symmetry argument, supersymmetry is the oldest but goodest solution to the naturalist problem. And then the other one is learning top-Yuga coupling, meaning that you don't expect the top-Yuga coupling persist all the way to the Planck scale. If it has a form factor that dies off at a certain scale, then you don't have this loop corrections above it. And then cosmological solution, you can regard it as a desperate action in counting the current situation. And so for this cosmological solution, the famous one is so-called relaxation. And then the second one I will explain is n-naturalness. As a final one, I will introduce this selection mechanism, which connect the dark energy, which is another big hierarchy problem or fine-tuning problem. Why our cosmological constant is 10 to minus 120 smaller than the natural size might be tightly connected to the weak scale in such a way that only when the weak scale is certain value, you are allowed to have a universe with a small cosmological constant. So this is the idea of weak scale as a trigger. And then in the meanwhile, I will also introduce my desperate attempt after Higgs discovery. And for each motivated BSM, there are signatures. However, unlike the standard signatures that you'd expect in colliders, I mean, you might have heard so many times that for this hierarchy problem, always for top, there is a top partner, either top or top friends, T prime, or some other particles. But that doesn't have to be always the case. So for symmetry argument, of course, the supersymmetry predicts top partner stop. But there are other cases where compositeness predicts the strong interaction at compositeness scale. And then so-called neutral naturalness, the partner doesn't have to be color charged. And even the color neutral particle can be an explanation for the cancellation of the loop corrections. And then for cosmological solutions, there is an action-like particle, relatively light, but weakly interacting. And in principle, you can be able to see it. And in this n-naturalness setup, basically the prediction or the interesting phenomenology appears somewhere else, not at the colliders. So this somewhere else means the order one deviation in delta n effective, meaning the cosmology, you might expect some dark radiation. And then there is a feebly interacting return. This is the particle that you can probe directly at the collider, but that interaction rate is so small, so you need the really ultimate colliders or whatever. And then the structure formation at neutrino mass scale, things like that. So I think nobody would connect the dark energy deviation with the hierarchy problem, but there are cases where you can connect all these interesting phenomenology. And the last one is the selection mechanism. And here, there is a definite prediction for the extremely light color, which is whose mass is kb down to 10 to minus 22 eV. And this extremely light color can be also a candidate for the dark matter. And then the other thing is Higgs boson always comes with its cousins. So you should be able to see the other Higgs here. So before Higgs discovery, I mean, this was the slide that I got from my LHCb talk 10 years ago or 15 years ago. And that at that time, everybody was talking about this motivated theories. So for motivation, you need naturalness, meaning why Higgs is so light. And then on the other side, there is a dark matter that we know it exists. It doesn't have to be the particle interacting with the cell model. I mean, if it is only gravitational interacting, we will never know whether, I mean, the identity of it. Nevertheless, I mean, this constitutes a big part in BSM construction. And the third one was unification. Nowadays, no one is mentioning it. So I will just remind you of this unification of gauge couplings. So here is a very interesting, remarkable statement that charge quantization. I mean, you might consider this neutral atom to be granted. Nevertheless, it is not granted at all. And the fact that d quark has charge exactly 1/3 and up quark 2/3 just to make the atom to be neutral. And this works in a high precision, and nobody knows whether there is any deviation there. However, as a theorist, if you work for the anomaly cancellation, and also if you work for the grand unified theories, you know that all these quarks and leptons are gathered into a single multiplet of higher gauge group, like SU5 or SO10. And there, this charge quantization or the neutral atom comes as a theory prediction that the trace should be 0 for SU gauge group. And therefore, this nice aspect should persist. That's what I believe. And furthermore, I mean, this might be just a miracle or just a kind of accident, but these three couplings of strong, weak, and electromagnetic interaction just meet at some scale, meaning that all the couplings are defined as a running coupling. And if you just go to a higher and higher energy, short distance, then they share the same size, meaning that it is very plausible that they might come from a single coupling, which is unified. This was the idea of grand unification. And original grand unification idea was dead because the proton decay experiment didn't find any proton to decay. However, if you combine it with the supersymmetry, then the prediction really went up, and then it is still consistent with the current experiment. So why this accidental observation is interesting? Because first, if it is not parallel, of course, two lines meet at one point. That's not very surprising. But three lines meet at one point is slightly surprising. And that meeting point is in between the Planck scale and the proton decay bound. And that's really a surprising fact that we still believe that this should be the correct picture. And then it was right before Higgs discovery. Many people were discussing that something is wrong with the Higgs search or a SUSY search, because if there was a natural supersymmetry, then it had to be discovered that lacked either supersymmetric particles or the Higgs boson. However, the lab bound 115 GeV was already too high for the natural supersymmetry to survive. But at that time, I think people mostly considered what is called M-Sugura or some universal gauge couplings, universal particle masses or things like that. And then I focused on what is the essential ingredient contributing to the fine-tuning? I mean, the Higgs mass loop contributions. And there were two things. One was the mass of the Higgs partner, so-called the Higgs inner. So that had to be light. So the Higgs, the partner had to be very light. And then the other thing was the top partner. And that had to be as light as possible in order to reduce the loop corrections coming from top partner. And in addition, I mean, this top partner had to have a mass splitting because there is an extra threshold correction coming from the stop mixing, which can increase the Higgs mass a lot. And therefore, that was really essential. And then the prediction was basically Higgs should be at 115 GeV in order to be natural. And then stop should be around 300 GeV with mass splitting of M top. And then also there should be a partner of the Higgs. And even in that case, fine tuning could be about 10%. And if you go further, after Higgs discovery, basically the situation really went worse, that the mass was 125, not 115. And this 10 GeV difference, you might think that it's very small. However, it's logarithmically depending on the Suji breaking scale. And therefore, basically, your stop had to go up to TeV. And even in the best situation, your fine tuning can be worse than 1%. So there is no way to understand this situation in supersymmetry in a natural way. So that was the situation. And if you just summarize all possible ideas explaining light Higgs, and then I would say that in this triangle, if you put it in the bottom, then from mg to tb, they are cut out, and also technically is out, and therefore we have a very small parameter space. All the way up is the Snell model. So the most natural place is here, and all these natural places are gone, and we are in a puzzle. This is the situation. And this is a famous plot by Alex Pomerol. And you see that I told you that for lab constraints, I prefer that this had to be a place for the Higgs, but it didn't come up with that. And 125 is exactly in between the preferred region of two different main ideas. And of course, it is consistent with the Snell model. So we have no idea which is the right direction. And for this, my psychological reaction was, so we were so much brainwashed by the community that supersymmetry had to be there and everybody believed it, and therefore I was brainwashed. So forget about everything, start from the beginning, what you can think of. And then the first attempt was, so forget about the mass. Imagine that there is a world without mass. I don't know what can explain it, but if you only have the quadricoupling of the Higgs, and then you run it down, and there might be a radiative correction which can provide you the electroexchange breaking. So this is the original idea of Steven Weinberg. At that time, when W and G boson was there, actually that was a mechanism for the Snell model, where Higgs mass is loop suppressed compared to W and G mass. Nevertheless, we already observed the top quark, and this top Yugawa gives exactly the opposite behavior, that your quadricoupling is growing as you go to low energy. I mean, if you start from the weak scale and go up, then actually it goes to negative. That's the situation for the Snell model. And therefore, I mean, this idea was not working in the Snell model. Instead, if you are introducing another scalar with a mixed quadratic, then you can realize the same situation like what W and G did for you. So you start with the positive quadricoupling and run down, and the coupling turns into negative value, and then you can explain the electric spin breaking without relying on the mass parameter. So this is a kind of alternative I was thinking about. And then you immediately see that there is a Landau pulse appearing just at multi-TeV scale. So this is really a bad theory. You cannot imagine that you can live with that. Nevertheless, you can be more smart in a way that if you couple it with the gauge interactions, and you can tame the interaction in such a way that you can postpone the appearance of the pole up to the Planck scale. So in principle, this is possible, and this is a kind of viable option. And in this scenario, actually, you can predict that the cubic coupling of the Higgs or quartic coupling of the Higgs can be significantly different from what is predicted in the SRA model. So in the SRA model, there is a quadratic and quartic coupling that determines everything. But here, it's just a logarithmic potential that determines everything, and you get a significantly different prediction. This is another reason why you have to measure this cubic quartic coupling precisely. And I introduced a singlet, and this singlet has a mixed quartic coupling with the Higgs. And this is what is driving your quartic to be negative at the weak scale. And then, so by itself, basically, you blow up immediately. And then you introduce another gauge coupling for the hidden sector for the singlet S. So singlet S is not a singlet, it's a scalar charged under some hidden gauge group. And you can use those hidden gauge coupling to tame all these couplings. Otherwise, this separate coupling of S just blows up. So you tame it with these gauge couplings, and eventually you can make without relying on the mass terms. That's what I'm saying. Yeah, radiative corrections. So if you start from here with a certain quartic coupling, and then at the weak scale, your lambda h, the quartic coupling of Higgs, turns into negative, and then you get an electric spin breaking. So that's a possibility. New particles are here, TeV. Yep. Yeah, this is just a beta function that you can play. Yeah. I don't buy this idea, but at that time, I mean, it shows my psychological reaction to the Higgs discovery. That's why I. All right. Okay.
The scale of this instability is not known. So I realized that maybe you were 10 years ahead of time.
Yeah, yeah. But I don't think there's anything deep here. I mean, it was my exercise, and oh, sure, yeah, yeah, yeah. And then the other one is among these radiative corrections, how to make this 1% fine tuning into 5% or 10%. I spent several years of trying to improve this tuning, and then I ended up with this learning Tabuga coupling idea, which I gave a talk several years ago here, but didn't come up with any paper. But the idea is very simple, that your Tabugawa can couple with some strongly interacting sector, and then this compositeness might rescue, but it will just improve your percent tuning to 5% and not more than that. And therefore, I don't think this is another big improvement. And then let's go to the main topic, which is a cosmological solution. So the relaxation is a nice idea in the sense that wherever you started from, there is a kind of scanning field, scanning scalar field, and you have a tilted potential, and then it rolls down, and eventually below zero potential, there is a kind of wiggle developed depending on the electroweak scale, and you stop here. And that's the case, then you don't need to explain why this scale is so small compared to the fundamental scale. Nevertheless, if you look at the mechanism, then always you find that this height of the potential given by, so this is a slope of the potential. So slope here is given by the excursion that this phi should go, and then the fundamental scale that this phi started from, the potential to the lambda to the force. So suppose that this fundamental scale is very high, and then this should be comparable to this f, the size of this wiggle, and then the height of this barrier. And from this simple relation, you end up with the conclusion that, so for the weak scale, 100 GeV, if your cutoff is in the most conservative way, 10 TeV, and still you end up with the 10 to 8 on the left. So your excursion of phi should be 10 to 8 times your fundamental, F. So it's like a trans-Planckian excursion, which is extremely hard to imagine. So I don't want to add more, and I will go to n naturalness. So this is one way of think about the problem, that there is a dot, and there is a very special point where the dot was located. And then what's the chance that you randomly throw the dot and ended up with a very special place? This is a kind of fine-tuning problem. The other way of phrasing fine-tuning problem. And for a single dot point, it's very hard to explain. However, if you throw your dot as much as possible, then basically you fill out all the places, and no matter where you are looking for, always you will find this dot position. And it's that simple. So in some sense, this is not very different from the multiverse idea. So suppose that there is a multiverse where the Higgs mass varies arbitrarily, and then whenever you have enough multiverse, your explanation is done. However, it's not a science. There would be no observable consequence, and you will never know whether it's the right explanation or not. And then the real idea came from the fact that it doesn't have to be in the multiverse, but it could be in our universe. So suppose that it is in our universe where there are many copies of the star model with different Higgs masses. And then that copies Higgs masses vary differently. And then one of them will have a very small Higgs mass. And in that way, we can understand why the Higgs mass is so small. And I should mention that this idea is stemmed from large extra dimensions. And then large extra dimensions, the essence is you introduce lots of degrees of freedom. If you introduce lots of degrees of freedom, you can lower your fundamental scale and solve the hierarchy problem. With Michel and Ghiattopalli originally put the idea. However, if you have this much degrees of freedom, you don't need, this much copy of the star model, but you don't need this much. The idea is just the square root of it is sufficient to realize the scenario if the Higgs mass scans, because you lower your fundamental scale by this amount, 10 to 10 GeV, the intermediate scale, by having many degrees of freedom. In addition, your Higgs mass scans, and one of them will have 10 to minus 16 compared to the natural one. And therefore, it's a hybrid explanation of why you ended up with a very small Higgs mass. And this is scenario one, but you might think 10 to 16 copies of the star model is too crazy. And I think a more realistic scenario would be 10,000 copies. And if this is the case, we have an interesting prediction that the fundamental scale should be 10 to 16 GB rather than 10 to 18. And then the fundamental scale is 10 TB rather than 100 GB. So there might be a small gap between the weak scale and the scale that we are probing the new particle. So this is a cartoon picture that all the stellar model sector, SU3, SU2, U1, and quarks and leptons are existing. I have, yeah. Okay. And then the other one has their own gauge group and their own interactions. And they don't talk to each other except what is called return. And that return is something that carries all the energy density of the universe after inflation. And when this return decays into the stellar model particles, the interaction is governed by through the interaction with the Higgs. So for each Higgs sector, they have different Higgs masses. And when return is lighter than the lightest Higgs mass, basically the effective interaction always comes up with the inverse Higgs mass square, or the quartic power of it. And therefore, as you go to a heavier Higgs sector, your branching ratio from return is suppressed. And therefore, you ended up with the preferentially decaying into the lightest Higgs sector. So you just populate the energy density of the lightest Higgs sector, but you have a very tiny off energy at the other sector. So the collider thinner is this M5 is slightly lower than the lightest Higgs mass. And then the problem is this return coupling is extremely small in order not to ruin this mechanism. And also the coupling of the return with the Higgs is less than 10 to the minus 6. So the prediction is, if you naively think that for the next sector, they also have photons and neutrinos. And if you just naively count delta N effective, it's 7.4 from neutrino and photon. However, the branching ratio is 10%, and therefore you end up with delta N effective 0.7. But I mean, you can play this game, and your naive prediction is order 1 delta N effective, but it can be as low as 0.1. And the other way, you might have some objection of why do I introduce such many degrees of freedom? And if you are familiar with this extra dimension, one extra dimension, you can discretize it. And on the lattice, basically, you have so many sites existing there. And then this n copies are just a different phase of that extra dimension. When this link field get a wave, it's an extra dimension. If they don't get a wave, then it's just n copies. That's one way of understanding the situation. So as the last one, I will explain this weak scale as a trigger. This is, the idea is extremely simple. You imagine some scanning parameter which depend on the weak scale. In the stellar model, we don't have one because H dagger H is gauge invariant. It carries no charge, and therefore it is dominated by UV. So the minimal choice that I can make is to introduce the second X and go to 2X Doppler model. And when this H1, H2 Oh, so I should have control over this parameter. Otherwise, I can just close the loop for the tadpole. So suppose that I have phi, which is affected by the Higgs wave, phi H1, H2. But if it is phi H dagger H, then I can just close the loop, and it just generates the tadpole for phi. So it doesn't depend on the Higgs wave, but it's just determined by the cutoff. So I should have a control over my scanning parameter. It's a G2 that, yeah, the simplest. So I can, so in this 2X picture, I can think of the space where the m square is negative for one Higgs and negative for the other Higgs, then for sure, these two get a wave. But even in this side, they get a wave because we have lambda QCD. And always, even if this mass is positive, this tether pole coming from QCD, electric symmetry breaking, generate the wave for the other Higgs. So the schematic picture is like this. And then basically you can imagine that there is a very special window for this order parameter, which allows you to have extra scanning for the cosmological constant. So the big picture is you have a world where your cosmological constant has a very sparse scanning, let's say TeV to the fourth. And then your cosmological constant should be that big. And then only after electric symmetry breaking, you can do the extra scanning and then end up with a very small cosmological constant. That's the idea. What is going on? Yeah. So the idea is basically you have a degenerate vacuum for phi, so phi square minus m square to the square. For each phi, you have a degenerate vacuum, and there are n phi of this scalar particle. Then you have a huge degeneracy. And then this phi couples to H1, H2. So whenever H1 get a wave or H2 get a wave, you have a tilting of this degenerate potential. And that tilting generate the degenerate vacuum into those splitting. And if this splitting is big enough, you cover zero in the scanning of cosmological constant. And then if it is too big, basically your tilting eliminates the other vacuum and you ended up with a single vacuum and you just go back to the original vacuum. That's why there is a window, special window where the Wick scale is allowed to vary from here to there. And of course, this is given by your input parameter. But if you imagine this world, then there is a very concrete prediction that this small cosmological constant is possible or compatible only with a certain window of the Wick scale. So then Wick scale has a very special meaning that if we are living in a universe with a small cosmological constant, then Wick scale should be here. And especially, I should emphasize that this Wick scale has a flat distribution, meaning that from mu s to mu b, any place is equally preferred. So it's not like a quadratic or quartic sensitivity to high scales. So this is the idea. And I would say that there is a very interesting collider pheno. That still there is another Higgs particle hiding there, waiting for our discovery. And the other clear indication is these phis. There are hundreds of phis, but they are extremely light and even can be served as dark matter candidates. So I think I'm almost done. And the main message is my belief on physics, even after trying all these possibilities, which are unconventional compared to the conventional one, I still believe that Wick scale supersymmetry at multi-TeV, without having this complicated structure, might be there. And it is just beyond the horizon that we can see now. We need a taller tower to extend the horizon. There was nothing wrong for theorists, but it was the fault of the experimental capabilities. That's what I'm hoping. And if we can build a bigger collider, and if it is at 10 TeV, we'll be able to see it. So just make the tower to be taller, or can you bend light, or is there any mirror that without having tall tower, can you probe it? There might be ways to think about it, but this is the direction that I'm pursuing. Nevertheless, it's very depressing in the sense that for good physicists or for good scientists, the best, the first condition for you is you should find the right topic that you can do in your life. And then I did the wrong choice. And so if it is 10 TB, I should wait for 50 years or 30 years. If it is at 100 TB, I should wait for 100 years or 200 years. We don't know. So unfortunately, this is the situation that we have to wait too long compared to physicist lifetime. And then the last remark is, so for this 10 to minus 3, 10 to minus 4, this is a very small number, but how small it is? I think there are certain cases where this charge quantization is nicely explained by grand unified theories. So if it is that much tiny, it should be 0. And then also, I think most of people believe that photon mass is exactly 0, rather than it has a tiny breaking at EV or whatever. And for observation-wise, also historically, when Kepler just found out his law of elliptic motion, everybody believed that this motion is circular because it was so close to circle. However, that was based on the misconcept. And this eccentricity is not exactly 0, but it's very small. And also, we know that this naturalness argument was taken as a bad example by taking this parallax. So when we were concentrating on this geocentric motion, people couldn't move on because there was no observational parallax. If the distance from the nearest star is comparable to the second nearest star, if it is, that ratio is order 1, then we should be able to see the parallax coming from the second star. But we haven't observed it. And then there are two possibilities. One is this ratio is so small. The second nearest star is too far away, or the Earth is not moving. And people ended up with the second conclusion, which was wrong. And historically, this is huge. 1 AU for the solar system and 270,000 AU for the next nearest star. So we already observed this huge number. And why is it so? If we are living in a binary star system, then life cannot survive there, right? And therefore, this next nearest star to nearest star ratio cannot be order 1 for the life to survive. So is there a certain criterion to believe that it is 0? I think all these examples, even the last one, which I found it very interesting before observing this dark matter, many people consider that this density perturbation, the inhomogeneity in CMB had to be observed at 10 to minus 3 level, but it was not observed even at 10 to minus 4, and it was regarded as a crisis in cosmology. And the solution came out with the dark matter because dark matter just evolved its structure way before the recombination. And all these small numbers are related to the observer in some sense, entropy principle. So I think also there is a way that we might think about the weak scale. If there is this number, then it's related to our observational effect, maybe. Yeah, I have 2 slides. Yeah, so I came up with one toy world to imagine the current situation, why we don't observe any new physics at the weak scale. And then you can imagine the world where there is an electron with electron mass, but pion is, let's say, 10 MeV. And then QCD scale is, let's say, TeV. And your charged pion is slightly below TeV. And if your reachable energy scale is 10 MeV, you will only see pi 0 and nothing else. And from that world, can you imagine the structure of up quark, down quark, and QCD and all the electric symmetry breaking? It's almost impossible. You will just invent your supersymmetry with the pions. Then it's a failed story. I think there are many possibilities that we are still missing informations. And the last slide is this. I was working for physics working group for International Linear Collider and gave a talk on the status in 2015. It was right after Higgs discovery, but when everybody was excited about 750 GeV diphoton excess. And then I found that people started to discuss photon collider at 750 GeV. And I thought that it's ridiculous. I mean, we are talking about the Higgs collider because the Higgs is so special coupled to every particle. But for pion and QCD, if you just build a 10 MeV collider for that toy world, what did you get? Nothing. And that was my impression. So I think still the information that we got from collider is too small. So I should be humble, but at the same time, don't give up. And also there are other topics, monopoles that I'm working on right now, which is nothing to do with the colliders, but of interest of its own as a theorist. Thank you.
We got some time for discussion. In the meantime, I might ask if you can go back to the list of things that were small because of the observer. I think I may agree, but yeah, this one.
Yeah.
So sometimes is the observer where it's located. Sometimes it's the fact that the observer exists.
Yeah, I think we have no idea for this.
Uh-huh.
And for this, it's just we are living in an old solar system. So initially, the eccentricity could be big, but after the collision,
Eventually.
only the system can survive with a small eccentricity. So it shows the history. And then this one clearly shows that anthropic principle. I mean, binary system is so violent that life cannot survive. And therefore, it's not just the order one number, but it should be bigger, I mean, smaller than something in order for the life to...
some star moving too fast, you're not gonna see it next.
Yeah, you will be kicked by another star.
Yeah.
Star, you mean the sun, which was which was not a star according to the...
Yeah, sorry. Yeah, right? This is sun. 1 AU is the unit for this. Yeah, sorry. Yeah.
In modern notation.
The argument that they actually made, they did make the argument and before all of this, and it was just that it was a ridiculous number. It was not, it just seemed like it had to be very, very
large. I know that
they'd estimated the distance of the sun.
Geocentric school, there were reasons for them to believe that because the Earth is too big to move, and then there are many other reasons which are also scientifically justified. So we should not be fooled by natural number. That's one lesson. Yeah.
Another comment. I mean, the lesson from the eccentricity, though, is not about it being a small number, because the thing is that in Kepler's time, they had to fit the orbits, they had to introduce all sorts of epicycles. And in fact, one of the objections to Copernicus's original work is that it didn't fit as well. The precision data didn't work as well. Okay, and so
the thing is
that Kepler, half of Kepler's discussion is trying to convince himself that the ellipse is as beautiful as the circle.
I see.
I mean, it was some mathematical beauty kind of thing, actually.
That was the
sticking point.
Kepler model, the polygon thing. So it was the same guy who thought that this polygon explains the distance between all the planets.
By mathematical beauty.
Eventually ended up with the ellipse. Yeah. You're not talking about particle physics, but
but still there are lessons that one could actually take from this. I had a curiosity on these models with many copies, including n-naturalness.
Yeah.
So the TeV scale is just because the TeV is the scale. It doesn't really come out of anything.
No.
Correct?
No. Yeah. Yeah, correct.
Okay. So it's a
I think so it was motivated from those dark energy signatures. So whenever there is some delta ineffective, let's say 0.5 or 0.3, people came up with random relativistic particles to explain it. However, I mean, whether you can connect it with the central problem in particle physics, and then in this picture, it is coherently understood. So in that sense, it's a qualitatively different from just ambulance chasing. Once you observe some deviation, just introducing one particle is sufficient, or you try to understand in a bigger picture. That's
well, I didn't mean to necessarily criticize. I was just trying to understand the following. Maybe people in the room have different opinions, but when do you ever predict the actual scale? Basically, you actually invent a mechanism that explains some scale, but eventually you need to tell from data where
I'm on this toy world. I mean, we just have pion. What can you tell about lambda QCD or the complicated structure at high energies? I think even genius cannot imagine what would be there. But if you didn't have all these,
yeah. So I think this. I mean,
yeah, but why you are describing just the electron pion interaction with the chiral Lagrangian? I don't see it. So it's just one of many possibilities that is explored, that can be explored at that 10 MeV world. And then I'm just illustrating it as an example. That's what I'm saying.
This is precisely the example where you have really many UV completions that.
Yeah, but all the attempts that we did up to now is a kind of simplified version, just a few. And then in order to go further, you need some extra information. That's what I'm saying.
Can a model like that really come from a QCD-like theory? Because I didn't want to ask, but
no.
It's between neutral and pi
plus, plus, E minus, and one scalar. That's it. And then from there, how can you imagine the QCD structure there? I don't.
Okay, so you're not necessarily buying the pi plus to be connected to the pi zero as it is in our case. Okay. Maybe I understand better what kind of analogy you're trying to make. Do we get any more comments for Hyung Do? Seems that we don't. So we thank you very much.